What happens to a function when x gets absurdly, unreasonably large? Not large like a million, large like keep going forever and never stop. That's what a limit at infinity measures, and once you know the trick, you'll be able to solve these in your head faster than you can type them into a calculator. Infinity isn't a number you can plug in, it's a direction. So the limit as x approaches infinity of f of x is really asking, as x keeps growing without bound, what does f of x settle toward? Start simple. The limit, as x approaches infinity of x squared. As x grows, x squared grows even faster. There's no ceiling. The answer is positive infinity. Now the limit as x approaches negative infinity of x squared. Here's the twist. Squaring a negative number makes it positive. So even heading toward negative infinity, x squared still explodes toward positive infinity. The limit as x approaches negative infinity of x cubed. Odd powers keep the sign. A huge negative number cubed is still hugely negative. The answer is negative infinity. The takeaway: even power terms dominate toward positive infinity on both ends. Odd power terms flip sign depending on direction. Here's a shortcut that will save you a ton of algebra. When x is heading toward infinity, the term with the highest degree completely dominates every smaller term. You can basically ignore everything else. Example: the limit as x approaches negative infinity of 5 plus 2x minus x cubed. Compare the terms. 5 is a constant, 2x grows linearly, but x cubed grows fastest of all. So for huge x values, this whole expression behaves just like negative x cubed. As x approaches negative infinity, negative x cubed approaches positive infinity, negative times negative infinity. Answer: positive infinity. Try another. The limit as x approaches negative infinity of 3x cubed minus 5x to the fourth. The x to the fourth term dominates x cubed. The expression behaves like negative 5x to the fourth. Any negative number raised to the fourth power becomes positive, so negative 5 times positive infinity gives us negative infinity. This is the single most useful pattern in this entire video. When you have a fraction of two polynomials and x is heading to infinity, compare the degree of the top to the degree of the bottom. There are only three possible outcomes. Case 1, bottom heavy, where the denominator's degree is bigger, the limit is always 0. Example: the limit as x approaches infinity of 5x plus 2 over 7x minus x squared. The denominator's degree 2 beats the numerator's degree 1. The answer is 0. Why does this work? Picture 1 over x as x grows. 1/10 is 0.1. 100th is 0.01, 1000th is 0.01, shrinking towards 0. A more bottom-heavy fraction shrinks even faster. Case 2, same degree on top and bottom. The limit is simply the ratio of the leading coefficients. Example: the limit as x approaches infinity of 8x squared minus 5x over 4x squared plus 7. Both are degree 2. Just divide the leading coefficients. 8 over 4 equals 2. Case 3, top-heavy, where the numerator's degree is bigger. The limit is either positive or negative infinity, never a finite number. Example: the limit as x approaches infinity of 5x plus 6x squared over 3x minus 8. The numerator's degree 2 beats the denominator's degree 1. Since the leading terms are both positive, this shoots to positive infinity. 3 cases. Compare degrees. Done. You genuinely don't need to do any algebra to get the right answer this way. Though if a teacher wants shown work, you divide every term by the highest power of x in the denominator. And every term with x in the bottom shrinks to 0, leaving you with the same answer. Let's slow down and show the proof method for one problem, since you may need to show your work on an exam. The limit as x approaches negative infinity of 5x minus 7x cubed over 2x squared plus 14x cubed minus 9. The highest power present anywhere is x cubed. Divide every single term, top and bottom, by x cubed. The top becomes 5 over x squared minus 7. The bottom becomes 2 over x plus 14 minus 9 over x cubed. As x approaches negative infinity, any term with x in the denominator shrinks to 0. What survives? Negative 7 over 14, which is negative 1/2. That matches exactly what the compare leading coefficients shortcut would have told us instantly. Both top and bottom are degree 3, so just divide negative 7 by 14. Here's the payoff. A horizontal asymptote is a flat line the graph hugs as x runs off toward infinity in either direction. And finding it is literally just calculating this exact kind of limit. If the limit as x approaches infinity of f of x equals b, then the line y equals b is a horizontal asymptote. Example for f of x equals 5x plus 8x squared over 3x plus 2x squared plus 5. The same degree shortcut gives 8 over 2 equals 4. That means the graph flattens out toward the line y equals 4 as x runs off in either direction. No graphing required, you found the asymptote with one division. First, the limit as x approaches infinity of 4x cubed plus 2 over x to the fifth minus 1. Bottom heavy, the answer is 0. Second, the limit as x approaches infinity of 9x to the fourth minus x over 3x to the fourth plus x squared, same degree. The answer is 3. Third, the limit as x approaches negative infinity of 2x to the fifth plus 1 over x squared minus 4, top heavy. The answer is negative infinity. So let's recap. Infinity isn't a value to plug in. It's a trend to describe. For polynomials, the highest degree term dominates everything else. For rational functions, compare degrees. Bottom heavy goes to 0. Same degree gives the ratio of leading coefficients. Top heavy goes to positive or negative infinity. And these limits are exactly how you find horizontal asymptotes without graphing. Next up, the opposite scenario. What happens when x approaches a specific finite number, but the function blows up toward infinity anyway? That's where vertical asymptotes and infinite limits come in, and there's a fast way to figure out the sign every single time.